Okay. So next up is the integrals yielding in hyperbolic functions. So for this part, all you need to do is to apply substitution method and um, choose the appropriate value for u so that you will end up with the following form of integrals, and then apply these integrals to get the inverse yielding the integrals yielding hyperbolic functions. So actually, you usually this integral does not show up in the exam. So most probably the ones that will show up will be this six, the first six, and then these two. It's very rarely na this one and this one shows up in the exam. But I still I'm encouraging you to memorize all of these integrals as much as possible. Okay. So next, let's show some examples solving the integrals yielding hyperbolic functions. So for number 3, we have the integral of hyperbolic sine of cotangent inverse of x all over x squared plus 1. So as you can see, we can let u be equal to the function inside hyperbolic sine. So that is cotangent inverse of x. And then the derivative would be negative 1 over x squared plus 1 dx. Therefore, our integral is equal to negative of hyperbolic sine of u du. Kasi we can divide this one by negative 1 to get 1 over x squared plus 1 dx equals negative du. And then this one is this part of the denominator. So this will become du, and then the function inside u, hyperbolic sine will be u. So we have integral of negative sine, hyperbolic sine of u du. The integral becomes hyperbolic cosine of u, and then plug in the value of u. So that is cotangent inverse of x, and then add plus c. Next, we have another example. Hmm? Wait, is this the same number? Oh, okay. I'll answer another exercise. Mali pala yung number 3 ko. Copy the same. So, yung item kanina this one should be item number 4. And then this one should be item number 3. The third item is hyperbolic cosine wait. Should be hyperbolic cosine lang. And then log of 5x over 5 2 minus x minus 5 raised to x, and then dx. Apologies for the typo. That should be hyperbolic cosine lang of x. Okay, next, what we do is to let u be equal to log of 5x. This is, du natin is 1 over x ln 5. Am I correct? But we don't have that one. Okay, let's just skip that one. I'll find another item. Now, module. Please wait. I'm looking for another item to solve involving hyperbolic functions. Skip number 3. Ito puro mali yung mga. Yeah. Okay. I'll just look for another integral. Okay. 4.3, 4.3, 4.3. 4.3 exercises. Bakit wala? Wait. Okay. So let's answer this item. Cos squared x secant squared x dx. This is also squared. Okay. So for this item, we know that the derivative of cos of x is negative square of hyperbolic cosecant x. So we can let this one be u, and then this one is du, and then just add dx here. And therefore, we have integral of u squared, and then negative, divided this one by negative 1, we have negative du. So we just have the negative integral of u squared du. The integral is negative u, 2 plus 1, so that is 3 over 3 plus c. And then substitute back our formula, our value for u, which is hyperbolic cotangent. So we have cube over 3 plus c. Okay, I'll look for another exercise involving hyperbolic functions. Okay, wait. Okay, so we have another item from the module. This one. Number 15. It's not working properly. Secant x2 plus squared x dx. Okay. So for this item, I think if we let u be hyperbolic cotangent of x, then du equals negative cosecant x cotangent x. But we can't find this in the function. So this is probably wrong. What we can do is to actually distribute yung hyperbolic secant. So we have 2 hyperbolic secant x plus hyperbolic secant x, and then cos squared x dx. Then we can separate the two integrals. So we have integral of 2 hyperbolic secant of x dx plus the integral of hyperbolic secant of x hyperbolic cotangent of x squared dx. Note that for the first integral, we know the integral of this one from the list of our integrals. So that is this one. So I'll just copy this one, Control C, and paste it over here. Oh. Okay. I'll just exit this one, open again. Okay, I'll share it again. Okay. So that is this item. paste it. Then minimize. So note that this one is the integral that we will be using. So therefore, for the first integral, we already have 2 times quantity 2 tangent inverse of e raised to x, and then plus the integral of this one. But some technique that I usually do for this function is to rewrite this as sine and cosines. So hyperbolic secant is 1 over cosine of x. And then this one is, since it's cotangent, we have cosine squared x over sine squared x dx. Cancel. We have one remaining hyperbolic cosine here. So we have 4 tangent inverse of e raised to x plus the integral of hyperbolic cosine of x all over hyperbolic sine squared of x dx. For this integral, we can let u be hyperbolic sine of x. Therefore, du is hyperbolic cosine of x dx. I chose hyperbolic sine because this one is with square and it's also in the denominator. Usually, we let u be the terms in the denominator so that the derivative should be in the numerator. So this one is du. So plugging in, we have copying this one, 4 tangent inverse of e raised to x plus the integral of du over u squared. But this is u raised to negative 2 du. So the integral of that one is, wait, copying this one. So we have the integral of this one is u raised to negative 2 minus 1 all over 2 minus 2 minus 1. This is negative. Plus 1 pala. So this is negative 1 and then plus c. So we have 4 tangent inverse of e raised to x plus 2. So this is raised to negative 1 sine of x raised to negative 1 and then over 1 plus c. Rewriting this one, I have 4 tangent inverse of e raised to x minus 1 over hyperbolic sine of x plus c. Or 4 tangent inverse of e raised to x minus hyperbolic cosecant of x plus c. Note that I just used the first definition for the integral. You can use the second definition as well for the integral of hyperbolic secant of u. It's okay. So that is it. Thank you for listening.